Hello everyone and welcome to PrepFusion. I am Anish and today we will be starting the lecture 3 of this control system chapter, right? Of the first subject, that is the basics of control system. So in the previous lectures we studied Laplace transform, then we did bit of few LTI systems, what are LTI systems, and learned a few definitions, right? Fundamental mathematical tools for us to solve that are required in this whole chapter, right? So let's start with lecture 3. In lecture 3 we'll first learn what is a transfer function, then what do we mean by control of the control system, and what are different types of system, right? Open loop system, closed loop system. Then we'll learn about negative and positive feedback in a closed loop system. Okay, so these 4 topics we'll learn in this lecture. So before starting the lecture, right, I forgot to mention one thing from the previous lecture, that in a causal system there is also another definition for causal system. That definition for causal system, right, is that the impulse response should be 0 before t equals to 0, right? Before t equals to 0, the impulse response should be 0. Okay, that is impulse response h of t should be equals to 0 for t less than 0. Okay, then the system will be causal. Okay, and it should not be equals to 0 for t greater than equal to 0. Okay, these two conditions need to be satisfied, right? Like, or the basic definition we know that the output, right, should be depend on either the present or the past values of input, not on the future values. That already I have already explained to you, right? That already we have learned. Okay, so one more thing that we can say is, if my signal is causal, right, if my signal is causal, then the impulse response will always be a right-handed signal, that it should exist for t greater than 0 at the right side of the axis, not on the left side, right? So that also we can explain. So this thing I just missed on my previous lecture. So I already told you what systems we'll study in this whole subject, right? But let me write this down, that system that we will study in this whole subject. Okay, what type of systems we will study? We will study linear, time invariant, and causal systems. Previously I forgot to mention, like LTI I also mentioned in different times, but I forgot to mention it together. We will study, let me write this on, linear, time invariant, causal systems, right? So these type of systems we will study. Now let us come to the concept of transfer function. So okay, what is a transfer function? Like, the transfer function, right, is the ratio of the Laplace transform of the output to the input Laplace transform with 0 initial conditions. This is very important. Okay, with the 0 initial conditions. Like Laplace transform, I already told you, basically if we take the we are in a system and we have got the output response and we have given excitation. If I take the Laplace transform of the response and it is on the numerator and divided by the Laplace transform of the excitation, that is the input, then that will give us the transfer function. Okay, so transfer function of impulse response is also referred to as, Laplace transform of impulse response is also refers to as transfer function, right? Because the impulse response that we give, and what is the Laplace of impulse, right? What is the Laplace of impulse? It is 1, right? So in the denominator it is 1, and in the numerator it is y of s only. So transfer function t of s is equal to y of s only. So that's why it's telling that Laplace transform of the impulse response. What do you mean by the impulse response? If I give some impulse input, then what type of output I am getting? So yeah, that is y of s only. So let me explain this just in a brief manner. I will delete that. Okay, so basically it is telling us that numerator it is y of s, in the denominator it is a Laplace transform of input, right? And if the impulse we are getting, then it is 1 only. So that's why this is the transfer function only, right? This is the transfer function only. So t of s is equal to y of s only. Okay, so yeah, that's why this is what is this? This means the impulse response, right? Laplace transform of impulse response. So that's why this t of s equals to y of s. Okay, so yeah, this is one thing to mention. And like, what are the key points here to take note? That the initial conditions, right? Initial conditions should be 0. I hope you know what does initial conditions mean. Okay, so initial conditions basically, I think Himanshu has already taught you in transient, right? So t less than 0, and there should not be any like condition present in the circuit, any voltage, current, or something like that. Nothing should be present, right? Now, one more thing to note is that this transfer function, right? Transfer function is defined for only LTI systems. Okay, it is not defined for non-LTI systems. So, like, let me write this down. For LTI systems. Okay, so that's why it is very important to understand that in non-LTI systems we don't have any concept of transfer function. Okay, so yeah, this is one thing to note. And another thing to note is that initial condition equals to 0, that is, we will only see the forced response. Like, I hope you already understand what is a forced response and what is a natural response. Okay, so we will only see the forced response here, right? Forced response. Okay, so this is one important thing to note here. Okay, so now let us do one more thing, that like, why is this so like important to us, this concept of transfer function, right? Because transfer function is independent of output and input, just like the impulse response that I told you, right? The impulse response, if we know the impulse response, right, we can find the response for any type of excitation. That's why, like, the impulse response for any system is same, right? For LTI system it's same. That's the only reason here also transfer function will be independent of the output and input. Whatever may be the input, the output will come according to the transfer function of the system. So it will depend on the system only, right? So yeah, like, for any input we'll get the output according to the transfer function. So let me write this. To the transfer function, right? So yeah, this is one more point to note. Now, like, how can I write the transfer function as? So transfer function can be written as, let me write it in another color, n of s upon d of s. This is just I am trying to explain you one point, right? So this is the numerator and this is the denominator. Now this roots of n of s, right? Roots of n of s are known as the zeros of the transfer function, and these roots of d of s are known as the poles of the transfer function. So if you don't understand what is a zero, what is a pole, all this will come in at later lectures. Just write the name, okay, for now, and you will understand all this in later lectures. So, roots of n of s, let me write this, the number of roots, right? Number of roots. So m, and the roots are known as zeros of transfer function. And what is, like, this d of s, right? D of s, the roots of the denominator are known as the poles of the transfer function. So again, number of roots of d of s is equals to, let me name this as n. This is just a name, okay, nothing like there's some relation or something. This is just a name. And the roots of the denominator, right, they are known as the poles of transfer function. Okay, so yeah, these things you just keep in mind. Okay, now for a causal system, right, for a causal system, this condition should always be valid. For a, you should always keep this in mind, causal system, that n should be, or let me write this in different color, n should be greater than equals to m, right? So n should be greater than equals to m. Okay, so like why is this the case? Why is this the case that the number of poles, right, number of poles should always be greater than number of zeros? I will explain you with one example. Like another thing also, that for a realizable system and for a real system, right, the number of poles should always be greater than the number of zeros. Why? Because like I'm just explaining you, if you don't understand, that's fine. Okay, just for the people who want to know, because if the number of zeros is more than like the number of poles, then at higher frequencies the gain will become very high, infinity, which is not possible for actual practical systems. The gain reduces, right, gain reduces. So yeah, for that reason generally the number of poles is higher than the number of zeros. Okay, also for causal systems, our all real life signals are causal only. Okay, all real life systems until now at least they are causal. Okay, so for that reason also this number of poles will always be greater than the number of zeros. Okay, so yeah, let me do one example. So let's say I have a system which gives the output like this: y of t is equals to d of xt dt, right? I have a system like this. So what are the number of poles and what are the number of zeros for this system? So let me take the Laplace transform, right? Let me take the Laplace transform. This is y of s and x of s. So I hope you know how to take the Laplace transform of a differentiation. So it is s only. So this time, okay, let me do this in here only. Okay, then you will understand solution. So what is the number of zeros? It is 1, and number of poles is 0 only. Okay, so let me like write the draw the x, right? Draw the x, like x is a signal, right? It can be anything. So let me draw the x. Let me draw it in different color. Okay, let me draw it like this only. Okay, so this is just x of t, right, with respect to time. Okay, now what we are doing, we are taking the differentiation of this, and that is what the output is. So here what we can see, it is predicting the future, right? How? Like what does differentiation actually mean? Our first principles, right? What does it mean? Like from here also you are understanding, we are taking the slope, so we are predicting the future, right? Future values of x. Through that we are getting the input, through that we are giving the output, right? Or you can understand from equation also that what does this differentiation mean, right? X of t dt equals to limit h tends to 0 as x of t plus h minus x of t divided by h, right? This is the first principles. Now what is this x of t plus h? This is like we are predicting the future input, right? This is the present input and future input. So this is the y of t, right? So for finding the y of t we need the information of future input. Okay, for the present output we need the information of future input. So hence the system is non-causal, right? Non-causal. So that's why we see that the numerator, the number of zeros is more than the number of poles. Through this example it is hence proved, right? So yeah, through this also you can understand like why for a causal system the number of zeros should always be less than the number of poles. Okay, this thing you have to keep in mind. So now one thing I can do, let's say like I have another example. Let me take, I have one system, right? I have one system like this: t square y of dt square plus 2t dy t of dt plus 3 let me say 5 y of t equals to x of t. 5 y of t equals to x of t. Now, like, what you can understand here is the system LTI. Now in signals, in more better manner you will understand like how to find LTI and non-LTI. But whenever there is a time function, right, multiply it with the output or with the input either, okay, then this will be non-LTI, right? Anyways, you don't have to worry, because in control system non-LTI systems won't even come. But I'm just explaining you, this is a non-LTI, so transfer function for this won't exist. But we can take the Laplace transform we can take, but transfer function won't exist. Okay. System, hence transfer function won't exist, right? Transfer function won't exist, but we can take the Laplace transform. So don't just relate Laplace transform with transfer function. Transfer function exists only for a LTI system. We can take Laplace transform. Okay, we can take the Laplace transform. So this is another example. Let me take another example. So like, when we can't use this concept of transfer function, right? That's why I'm proving you. Don't worry, this won't come in like gate exam, but this is very important for practical knowledge, and someday they may play with something like this, right? Play with this concept. So yeah, so another example, let's say we have two systems, right? Okay, and both of them are getting added. I haven't taught you the concept of block diagrams yet, but just I think you understand this is just a simple adder. I hope you have studied your semester. If you haven't, don't worry, this will be covered in the next chapter. So this is just a simple adder, right? This adds two systems. Let me copy this. Okay, this is some issue with that. Okay, let me wait. Okay, the result became too big. Just wait a second. This is the adder. Okay, this is plus. Both of the signals are getting added. Okay, let me say this is system 2, right? And this is system 1. Okay, and let me say like I am giving the input as exponential signal e raised to power minus t ut. Okay, and the output, what output we are getting? We are getting y of t equals to, we don't know, we have to find out, right? So what are the characteristics of this system, right? So system 1, let me say system 1 is related as the output is related as like this only, t minus 3 into x of t. Okay, now what do we observe? This is a non-LTI system, right? This is a non-LTI system. So for this, the concept of transfer function won't be valid. So how do we find the output for a non-LTI system? That we will see. Okay, that we will see. And for the system 2, right, the output is simply let me write this in different way. So like this, 2 dy of t dt plus y of t equals to x of t. Okay, so this is the characteristics for the second system, input output characteristics. Now what do you observe is, this is a non-LTI system, and this is a LTI system, right? This is a non-LTI system and this is a LTI system. So simply taking the Laplace transform of this and taking the Laplace transform of this and then adding both of them up, and then like doing the inverse Laplace transform, or like finding the transfer function and then like doing the ratio, multiplying the inverse Laplace transform of the transfer function into this input, right? That won't happen. Like, sorry, not multiplying the inverse Laplace transform, the Laplace transform of this, multiply with that transfer function and then we get the output. No, it won't happen. It won't happen. Okay, so like what we need to do is we need to find the outputs in time domain for each of the case, then add them up. Okay, then add them up. Don't just find the transfer function and then do it. Okay, we can't find the transfer function for this one, right? Because transfer function doesn't exist for this non-LTI okay system. So what we will do is output for system 1, output for system 1. Okay, so what will the output for system 1? Basically the y of t equals to t minus 3 x of t. Now what is the x of t in our case? X of t is simply this one, right? This one. So e raised to power minus t ut. So just put the value x of t here normally. No like nothing fancy or something. So what will be y1 of t? Simply t minus 3 into e raised to power minus t into u of t. Okay, just do that. Okay, now output for system 2, right? Output for system 2. So what will be the output for system 2? So basically in this case, right, what we will do, we'll find the Laplace transform. You can solve it like that ordinary differential equation also, like that also in mathematics class, I hope you remember. But we can solve with Laplace transform. I will solve with Laplace transform. So I will take the Laplace transform, okay, of both sides. So like this side, right? Okay, let me write with different color. 2 times s of y of s, taking the Laplace transform of this one. I hope you have done practice of Laplace transform. So plus y of s x of s. Okay, so y of s, taking it common, 2s plus 1 equals to x of s. So y of s upon x of s equals to, taking half as common, s plus half, right? So this is the Laplace transform that I am getting. Now what is x of s in our case? Like x of t is e raised to power minus t into u of t, right? So x of s will be 1 by s plus 1, right? 1 by s plus 1. So x of s is 1 by s plus 1. So y of s equals to 1 by 2 we have outside, this is s plus half times 1 by s plus 1. Okay, so this is the like output Laplace, right? This is the output Laplace. So now what we can do, again we can do the like partial fraction thing and divide this into 2 terms, okay, to find the time domain expression. So half is in outside only, so putting s equals to minus half, what do we get here? S equals to minus half, we get like half in the bottom, right? Half in the bottom, so 2 goes up, so 2 divided by s plus half. Now putting s equals to minus 1 for this, like I hope you know partial fraction, we have already studied that in the lecture 1, I think lecture 1 or lecture 2. So minus 1 we do, okay, here we get minus half, so minus 2 goes over, so this is minus 2 by s plus 1. Okay, now what is this? S 1 divided by s plus half minus 1 divided by s plus 1. Okay, now what do you do? Take the inverse Laplace transform. So taking the inverse Laplace, right? So this becomes y2 of t becomes e raised to power minus 1 by t u of t minus e raised to power minus t u of t, right? Now we have to add these two up, right? Add these two up. So overall y of t will be, we have just simply added function at that node, right? At this node we have an added function, so we'll just add the outputs. So y1 of t plus y2 of t, okay, y1 of t plus y2 of t. What we can do is, what is y1 of t? Y1 of t is simply t minus 3 into e raised to power minus t, right? Minus t ut. And what is y2 of t? This is e raised to power minus 1 by 2 minus e raised to power minus t into ut, okay. So what is y of t? Y of t is simply t minus, so this is another minus e raised to minus t, so this is minus t u of t plus e raised to power minus 1 by 2 t u of t, okay. So yeah, this is what we get as our output. If you find the overall transfer function and then simply multiply this, like what you wanted to do, right? What you can, like, you wanted to do like overall transfer function, right? You do like t1 of s plus t2 of s, then you multiply x of s into t of s and you get overall y of s, then you take the inverse Laplace of this. No, the answer will be wrong for that, because transfer function for the first system won't exist, okay. So yeah, that was one thing to keep in mind. So let us do a few questions for finding the transfer function, right? So these are basic questions only, like you have studied all this in transient. I will just quickly recap the Laplace part, right? Recap the Laplace part. So like we have already done few questions, so this is the sixth question, okay. So let me take an example, like this is a basic circuit only. So we have one capacitor, okay, we have one capacitor C and R. If is it recording? Yeah, C and R, okay. And like we have one voltage source as like this V of t, okay. So what you have to do is find the ratio of V of s upon V of s. So Vi is the input, okay, V of t is the input and the V of t is the output, okay. Find the transfer function. Find, okay, let me just okay, find the transfer function of this, that is, okay, let me write like this only, V of s upon V of s. So like how will you find it? So I have already explained you that how to convert like capacitor into its Laplace domain, right? So first we will do that only. So let me copy this and convert this circuit into a fully Laplace domain, right? So let me recolor this and like this color, and let me do it like so. What will be C converted to? It will be converted to 1 by Cs, right? 1 by Cs, converted to 1 by Cs only. So yeah, and what will be this converted to? So Vi of s will be converted into, sorry, Vi of t will be converted to Vi of s, and this V of t will be converted into V of s. So let us do it bit quickly, okay, right? So this is simply a voltage divider, right? So this V of s will be simply voltage division times this R upon R plus 1 by Cs, right? So what will be the transfer function T of s? Simply like this. This is yeah, VO of s by V of s equals to R Cs by 1 plus RCS. So you can see it has 1 0 at s equals to 0, and it has 1 pole at s equals to 1 by RC. Okay, minus 1 by RC, that is. So yeah, the number of poles and zeros are same. So yeah, this system is a causal system, and this system is a practical. But if the number of zeros becomes more than more than poles, then the system won't be practical. You will not see any type of system up here in our passive circuits example, right? So like one more thing to take in note is that what do we mean by the order of a transfer function, right? So this is a first order transfer function. Like from here we will understand the concept of order of a transfer function. This is a order transfer function. Okay, so what do we mean by the order of transfer function? So let me write this down quickly. Order of transfer function, right? I'm writing transfer function in short. It is the, like there are many definitions for that. I'm writing it down. Number of independent energy storing elements present in the system. I hope Himanshu has already taught you this in transient, so I'm not going to like explain you this much. Okay, or you can say the number of independent initial values also. Number of initial values. Okay, number of independent initial values, or what you can say. Now this is you will not understand this, but we'll like study this in later chapters, right? Number of state variables, just write it down. Or what you can say is the order of the differential equation. Okay, so if I form a differential equation by this, right, the order of the differential equation will be the number of like order of the circuit, or like you can also say that it is a number of poles, right? Number of poles, how many number of poles are present, that also you can say. Just these are just the definition, not that important, but we need to know all this. Okay, so yeah, this is one thing. Now let us like do another example, like another example. Okay, I think that is it for this like example thing, because that will just waste your time. What you can do is, like, I'm giving you homework, you solve this, right? Solve these two questions. Firstly, you will tell me the order of the circuit, right? This is C1, C2, this is R, and this is plus minus V of S, and this is plus minus. Okay, so what you will do, tell me the order of the circuit. Order, okay. Transfer function you will find out, okay. And like how many independent energy storing elements are present here. Like we can see two elements that can store energy, right? Are they independent or not? Okay, these things you will find. Okay, so yeah, this is one homework question. Now another important question we'll come back to is this question, right? This is the 7th question. This is also an important question actually. So we have one R here, and C here, we have another R here, and C here, right? Okay, and this is input, this is the output. Let me just straighten this up a bit. So this is input, this is output. What you do is find the transfer function, obviously. V of S upon V of S. Okay, So what you might think that this is something like this is RC and this is also RC, so this is cascade of these two, right? Cascade of these two. So if you're thinking like that, then you're wrong. Why? Because there is some loading effect at this point, right? Because this current, right, is getting divided into these two, so the voltage will get reduced. So due to this connection, right, if this connection wasn't present here, then there wouldn't have been any loading effect, but there is some impedance here. So whatever I'm saying, if you're not understanding, don't worry. What I will do now, you will just write that, okay, due to this loading effect, we can't simply do the cascading like cascading of multiplications. What do I mean by that? I will explain in the next few slides. So let me write that. What do you mean by cascading? So what is the individual transfer function of this? So let me write this directly, that individual transfer function of this, right? Okay, let me copy this circuit actually. Individual transfer function of this, right, is simply 1 by 1 plus sRC. You find it, you will get this only, okay? And individual of this one also 1 by 1 plus sRC, okay? So if we cascade these two, then what will happen? Like you might say, yeah, just simply multiply these two, right? Cascading, I hope you have studied this in somewhere in semester or something. Cascade these two, then just simply multiply 1 by sRC times 1 by 1 plus sRC. So 1 by 1 plus sRC whole square, 1 by 1 plus sRC whole square. So this is wrong, this is wrong, this is not correct, okay? This is not correct. So here, due to loading effect, we can't do this, okay? Due to loading effect, we can't do this, okay? So how will we do it? Simply what we will do, first thing what you need to observe is that this is a second order circuit, because these two, right, they are independent of each other, like their voltages or currents are not dependent. Like this, I think Himanshu will teach you all these things, okay? So yeah, if they're independent of each other, then there are two poles in system, so order will be 2 in this case. So like solving this will be a bit difficult. What we will do, let me copy this circuit and I will assume a node here, x and y. We'll write the KCL equations, right? So KCL at node x, okay? KCL at node x. So it is Vx, this is I only, Vi only. Okay, let me like again convert this into Laplace domain, right? Okay, I didn't convert it to Laplace domain, I'm really sorry for that. So yeah, let me convert this into Laplace domain. This is S1, this is Si, this is S, okay, this is S1, okay. So yeah, this is S1, this is S1, okay, and this is S, right? So what will be this? So simply this will be simply, I'm not writing the S bracket S I will write at the end. You can follow this also, like in solving in your exam, right? You don't need to always write this bracket S term in your rough notes, like while you're solving. This is already understood, right, that this is we are solving this in Laplace domain. So this is understood for us. Like if you're writing in subjective paper in semesters, then you should always write it properly, but in like exams you don't need to write everything properly. Just you know that, yeah, this is Laplace domain, that's it, that's fine. You don't need to like make it more lengthier. So Vx minus Vi by R. Now what is this, right? So it is Vx by 1 by Cs, Vx by 1 by Cs plus Vx by 1 by minus y by R equals to 0, okay? So yeah, let me just like rearrange this. So Vx, I take common, 1 by R plus Cs is there any term of Vx? Yeah, plus 1 by r also is there, so this will become 2 by r only. Okay, then Vi, let me take Vi to that side, or what I will do, I will write Vx in terms of other things. So this is Vi by r also, so Vi by r, and we have Vy by r also, so 1 by r we can take common. Okay, Vi plus Vo, so this I can write Vx in terms of. So now what I will do, I will write the KCL equation at node Y. KCL equation at node Y, right? So if I want to write KCL equation at node Y, what I will do, like there isn't any current flowing here, right? Current through here is 0, so only this one, right? Only this one. So I can do, what I can do is simply voltage division I can do. Okay, so V Y, right, should be equals to Vx times 1 by Cs plus like R plus 1 by Cs, that is the transfer function that we previously wrote, right? Previously wrote, that is 1 plus 1 by RCS, right? Here this is 1 plus 1 by RCS, but this one wasn't, right? Due to this loading effect, right? Due to this loading effect, okay, this loading effect, this transfer function, right, this didn't come like simple terms, but this will come. Okay, because after this there is no loading effect, current through here is 0, that's why this come perfectly 1 by 1 plus RCS, but that won't come, that won't come. Okay, so what I can do is simply now replace this Vx, okay, and Vy is Vo only, Vx with this term, right? Okay, so yeah, let me first okay, let me, this R is in the bottom, right? So I will multiply this in the bottom, so Vi plus Vo divided by 2 plus RCS, right? Vi plus Vo divided by 2 RCS. So yeah, this is what we get. Now I will replace this Vx in this term only, so Vy is replaced as Vo, this is into 1 plus RCS. So I will take Vo on that side, so Vo I take common, 1 minus 1 divided by 2 plus RCS into 1 plus RCS, this term only, right? So let me copy this term only, and this is Vi. Okay, this is Vi. So what do we get? V equals to this term, right? This term is like 2 plus 3 RCS plus RCS whole square, so 2 plus okay, so this is Vi. So what is V over Vi? So V over Vi, right? Now we can write S, as we are in the final stage. This is 1 divided by 1 plus 3 RCS plus RCS whole square. So what we can observe is, this is not RCS plus 1 whole square. RCS plus 1 whole square was 2 RCS, in the middle term, right? It should come 2 RCS. Like if you expand this, this will come SRC square plus 2 RCS plus 1. But here one extra RCS is coming. One extra RCS is coming. Why? Due to loading effect, simply. So this is to keep in mind. But like now, if you draw it in block diagram, right? If I draw it in block diagram, what I can do? There is another square block present over here. Okay, so now if this is like the two transfer function, right? If I represent them as blocks here, okay, RCS plus 1 RCS, like in control system, right? What we assume, although it's like a very big assumption, but what we assume is that here, right here, there is no loading effect present, no loading effect present, right? Here there is no loading effect present, so then we can simply cross multiply this, right? So like this is, let's say this is Vi, this is Vo, this is Vo dash. What we can do, okay, what we can do is first find Vo dash over Vi. What is it? It is 1 by 1 plus RCS, right? Then what we know is Vo over Vo dash, it is also 1 by 1 plus RCS. Now this right, this doesn't change, this can simply get cancelled out. So multiplying these two equations, Vo dash over Vi times Vo over Vo dash, we get as 1 by 1 plus RCS whole square. So this comes out to be simply Vo by Vi. Okay, so here this is the answer, right? Okay, but in our case the voltage changes. Here there is no effect of loading effect. In like the second chapter also, block diagram, you will see like blocks connected in cascade, right? So they can simply be multiplied. There won't be any loading effect there. Okay, so yeah, this is one concept. So let us now learn about the control system. So I hope you have understood the concept of loading effect. Now we'll understand what is basically control system, right? What is control system? So what is the meaning of this control term? So firstly, like the definition, let us read. It is a group of physical components which gives us controlled output for any given input, right? For any given input we want controlled output. We just don't want any output, right? If I just turn on the fan and the fan moves like very fast and I'm getting cold from that, right? So yeah, I don't want that. I want it controlled. I want it to start slowly, then I wanted to control it in my in what speed I want, right? Let's say I want slow, so I will turn it on slow. I will get the regulator to knob, move it to knob 1, right? And if I want it fast, I will move it to knob 4 or 5. Okay, so that's why we want controlled output, or we want our desired output, right? So that is what a control system is. Okay, we want our desired output, we just don't want any output, right? So yeah, so this is, let's say this is an input, this is a controller, and this is a system, right? And the output we are getting, so input, turning on the switch, electricity is flowing in the input for the fan, right? Then what is the controller? Let's say it's the regulator, right? Voltage regulator, the knob, right? We rotate the knob, and according to that, the system, right? The fan, the motor, it goes to the system, the fan, the process. Then what happens? Output, what we are getting? We are getting the output as wind, right? We are getting the output as wind. Okay, so yeah, and to reduce the wind, we again control this, right? We control this, but this is an open system. Okay, there isn't any automatic feedback mechanism that can control this, right? What do you mean by open system and closed? Obviously we'll come to that in the next few slides. Okay, so yeah, this is what a control system is. Now what is a open system? So open system, as I already explained you, like this is a fan and we're giving to the controller, the regulator, and this controller, right, is giving controlled input to the system, right? Controlled input to the system. Okay, now in the open system, right, in the open system, the controlling mechanism is independent from the output. What do you mean by that? So whatever this output speed is, right, it isn't getting fed back to the controlling mechanism. So whatever the controlling mechanism is there, it will be there. Okay, it cannot factor in for outside disturbance. Okay, let's say like there is some outside wind, or let's say the fan blades have already dust in them. I am controlling the speed, but due to the dust, right, the fan is not rotating very fast, but it can't accumulate for that. It can't understand that the fan is not rotating very fast. I am changing the controller, I am changing the voltage regulator, but fan is not rotating very fast. Why? There is dust, but it can't take that factor into its account, right? Why? Because there is no connection between the input and output. Okay, and this is the open system. Okay, so can't factor in outside disturbance, right? Can't factor in outside disturbance. Okay, so like also what we can write is output doesn't know what is happening to the input. Just wait a second, one call is coming. Okay, what is happening here? Okay. Okay, so sorry for the interruption. So what are the examples of this open loop system? So what are the examples? So examples simply fan, as already mentioned, then washing machine. Okay, washing machine is also an open system. Like it doesn't know like if there are clothes or not. So if I am putting in clothes and turning on the machine, it will rotate. If I am not putting the clothes, still it will rotate. It doesn't know if there are clothes or not, all those things, right? Then automatic washing machine does know. So automatic term, yeah, it comes into the closed loop, right? And simple car, right? Simple car. So if I turn on the accelerator, it will just go fast like that. It won't see the traffic, it won't see the cars in front of it or side of it. It will just go fast. If I turn on the press the accelerator in my leg, right? So yeah, that is one thing to notice for a car, right? Normal car. Now let us come to closed loop system. So what do you mean by closed loop system? So in a closed loop system, right, we have a controlling mechanism that is dependent on the output. We have this sensor that measures the output, gives it back to the input, feeds it back to the input to the controller, right? And the controller like makes it so happen to get to our desired output. We want to get to our desired output, right? So in the previous case, like let's say the fan has dust, it won't rotate to our that speed that we want. The regulator will be on that third knob only, third section only, but the fan won't rotate to according to our speed because it has some dust and the blades have become heavy. It won't rotate. But if I take some like sensor, that would be very advanced. If I take some sensor and it knows it has dust, so what it will try to do is like clear the dust, right? Some automatic fan in future you may build something, right? Invent something. It will clear the dust and then we'll get our desired speed at 3 regulator. We'll get our desired speed. Okay, so yeah, so in closed system, the controlling mechanism is dependent on the output. In closed system, the controlling mechanism is dependent on the output. Okay, so yeah, or we can say for a closed system where feedback is present. Now it may be positive or negative. What do you mean by positive and what do you mean by negative? We'll come back. Okay, we'll come to in the next few slides. Feedback is present, where feedback is present. So like what do you mean by feedback? Feedback is a process of measuring variables that need to be regulated so that corrective action can be taken. So what is the measuring variable here? The measuring variable is the fan speed, you can say, or you can say the wind, that is the amount of wind that is coming, that you can say. So the sensor measures that wind speed, then feeds it back to the system, right? Like the controller or something. It says that no, it is not enough, the wind speed is not enough. So what it may do is it may change the knob, increase the regulator. Then the fan speed the fan speed may increase, the wind we are getting more. Then again the sensor sees it, then it says yeah, now it is enough, you don't need to increase the knob anymore, it will stop increasing the knob, hence we will get our desired output. Okay, so yeah, that is what we mean by feedback systems. So what is the advantage of this closed loop system? This closed loop system, right, are more robust to uncertainties and disturbances. Let's say some outside disturbances is coming, it will automatically take corrective actions to negate those outside disturbances. Okay, but what happens is this system, right, are more costly and complex to design. Okay, obviously if we are getting something, right, then obviously there will be some trade-offs. Okay, so here output knows what is happening to the input. Output knows what is happening to the input. So all these things I have like told you, you should write this down. You should write this down, or I can write like in very brief manner. Let me write. Process measurements that need to be regulated. Okay, that is what feedback is. Like we're measuring it, and like I will explain, this is a more robust, but here output knows what is happening at the input, right? What is happening in the input. Okay, so yeah, these things I've already explained you. I won't write it down, so it will take more time. But what are the examples of closed loop system? Anything automatic, right? Anything automatic system, it will be closed loop, because it will take some feedback from the sensor and this will give it back to, because it is automatic, right? We are not manually controlling it. We're not manually controlling it. The system itself is controlling itself, right? So anything automatic system will be closed loop, right? Okay, now let's say we have one fan that has a temperature sensor, right? Temperature sensor with it. So if it can measure the temperature, if we want higher temperature, then it will measure that, yeah, the temperature is lower, it will increase the speed, right? Also what it can do is measure the humidity of the room. It can either increase or decrease the humidity to increase or decrease the temperature. Okay, all those things will come into example of closed system, right? Also another example is self-driving car. Self-driving car. Okay, so now, like I will told you, like feedback is of two types that we will study. Now let us do the representation of closed loop system. So what does each term mean here? Okay, very important to understand. So this sensor, right? This sensor can be anything, right? This can be a like filter or machines. It can measure the speed. It can be a filter, like it is measuring some low pass or high pass signal. Anything, it can be anything. This sensor, right? Anything. Okay, so what do we call this? Let me write this in small. This is called as feedback path, right? This is called as feedback path. Okay, and what do we call this? This is called as forward path. Okay, so this path, right? This path is called as forward path, and this path is feedback path. The name is self-explanatory. Okay, so yeah, this is what this means. And at this point, right, at this point we are getting the controlled input, right? Controlled input. So input is getting controlled according to the sensor. It is coming, and what is this known as? So this is negative, right? If this is negative, we are subtracting. We're subtracting the reference input. This is known as reference input, the input that we are giving, but we have to make changes to the input so that we get our desired output, right? We get our controlled output. Okay, so to make changes to the input, if the temperature is low enough and I want high temperature, then we have to reduce that fan, right? So that the room becomes like hotter. Okay, so yeah, all those things. Input I have given very high, but I want the fan speed to be low. So obviously the feedback will give it some other input so that we can get some controlled input to the this system, right? To the processor. Okay, this is known as system, also processor, whatever you call it, it doesn't matter that much. Okay, or plant also they call it. So names don't matter, just this is a system. Okay, that you need to understand. So this is known as, all this is a terminology, not that important. Okay, for gate purpose, but still you need to know all this. So This is the error, right? This is the error. Okay, this is the error, this is the control output input. So all these things we have already studied. So as already told you, this is the feedback path, this is the controller gain GC, this is the processor or plant gain GP, and this is the output, right? This is control output. So we can write this as C of S. Okay, C of S. So all this we're getting. Okay, so yeah, can I now, what I need to do is find the transfer function for this, right? Transfer function for this. So I'll write this in one block only. Okay, block diagram, I hope you know a bit of it. If you don't know, don't worry, we'll study in the second chapter, but just bear with me for 10 minutes. This is very easier and simple to understand. So let me write this up pretty quick because the lecture is already gone a bit lengthy. Okay, so what I will do is represent this GC and GP, right? We will multiply, cascade these two and make it one block only. So this will be G of S only, right? This will be G of S only. Okay, now what is this? This is the feedback, right? This is the feedback. Okay, this is H of S, this is H of S. Okay, so sorry for the sound outside, sorry. Okay, why is this going that side only? So this is the I'm doing this for right now negative feedback system. We'll do this for positive feedback system. Okay, so this is just a representation of a simple feedback, right? Simple feedback. We'll do this for negative feedback system. This is R of S, reference signal input, and this is C of S, right? And this is the block diagram. So this is simply block diagram of a closed system, right? Figure. And what will be the transfer function of this? The transfer function that we call it, we call it as closed loop transfer function, CLTF, equals to T of S upon T of S, which is equals to Laplace transform of output over Laplace transform of input, right? Which is simply C of S upon R of S, right? C of S upon R of S. So this is what a block diagram of a closed loop system looks like. Okay, so I think this video is already got lengthy. So what I'll do is we'll learn the closed loop negative feedback and positive feedback in the next lecture, and then the open loop transformation, all those things, okay, in the next lecture. So let me just give a quick recap, but before that let me write this as figure block diagram of closed system. This is how we represent a closed system, right? Closed loop system. Okay, so yeah, this is the closed loop transfer function. I'm not writing the full form. So what did we study in this lecture, right? Firstly, we know we learned about the transfer function, right? We learned about transfer function. Before that, we learned about the another definition of causal system, that the impulse response should be equals to 0 for t less than 0 and should not be equals to 0 for t greater than 0. Then we did the learned about the transfer function. What is the transfer function? It is a Laplace transform of output over the Laplace transform of input with 0 initial conditions, and the system should be LTI system. These things you need to understand, right? And the transfer function is independent of input and output. Okay, it doesn't depend on the input or output. For a system, it is fixed. It will not change according to the input, according to the output. Okay, so yeah, again we learned that what are the zeros called and what are the poles called, and the number of poles should always be equals to or more than the number of zeros for a system to be causal. And we did one example also. Okay, did one example also. So here also we understood, like for a non-LT system the transfer function may not exist, but we can always take the Laplace transform. That is not an issue, but the transfer function won't exist for a non-LT system. Why? Because it is basically the Laplace transform of the impulse response. And impulse response, right, impulse response is like valid for all the systems, for LTI and non-LTI, but we are mainly like interested in LTI because impulse response doesn't change, right, doesn't change with input. Okay, with input. So for other systems it may change. Okay, so yeah, that is it. Then we did this system 1 and 2, and we did, like, we learned that they are, one is LTI and one is non-LTI, how to add those two systems. This won't come in your exam gate, but this is good for practical knowledge, and someday it may come, okay. So yeah, we did that. Then we did found out transfer functions of few basic normal RC circuits. Okay, also I told you the concept of auto circuit, so Himanshu has already taught you, but still I'm teaching you this, like telling you this because this is required in control systems. Then we did this very important example. Many people confuse this and simply multiply this with cascade, right? But no, we can't do it. We need to, because due to this loading effect. Okay, due to this loading effect. So we did that, we found out the results. Okay, but in block, right, we'll study this in next chapter only. If in block this is present, what we assume in control system is that there is no loading effect, so this voltage won't reduce, this voltage will remain same even if there is some block connected. If this block wasn't connected, then also the transfer function will be this. If there is some block connected, then also the transfer function will be this. Okay, the voltage won't change. Okay, so yeah, that is what we studied. Then we understood what is a control system. What does control mean? We want our output to be controlled, we want it to be desired, right? So we have to control the input so that according to that only we are getting the output. So there is one open loop system and closed loop system. So open loop, the output can't factor in any outside disturbance, right? Like there is some dust, there is some wind flowing anyways in the room, all those things it can't factor in for open loop. Okay, we need to manually change the controller. For a closed loop, yeah, it can factor in with a sensor. It measures the variable that we need to output variable that we want our desired output to be, right? Those things you can measure. Now we wrote few examples, and then we did the representation of a closed loop transformation. And next we'll study the transfer negative feedback and positive feedback and open loop transformation, and then other few topics, sensitivity and all those things, and we'll do few questions on that. Okay, so yeah, thank you for watching.